Okay, recording in progress. Start from presentation. The main task of aerodynamics. Main task of aerodynamics in aircraft development is measure forces and moments that act on aircraft. There are only one forces and one moment if we think about 3D space, but we must project this single force.
Hello.
Okay. Project this single force at 3 axes of coordinate systems. We have X, Y, and Z axis. And single forces in projection decomposed into 3 forces: lift, drag, and side forces. Same with moment. We have single moment that act on aircraft, and this moment decompose in 3 moments: rolling moments, yaw moments, and pitching moments. So main task of aerodynamics is calculate these 3 forces: lift, drag, and side forces, and 3 moments: rolling, yaw, and pitching moments. And what we can use for accomplish this task. We have 3 main methods of aerodynamics. There are theoretical methods, analytical methods. We have exact mathematical solution for simple problem like a delta wing, straight wing, lifting like theory, like 2-dimensional airfoil, and so on. But this method exists only for simple problem. When you talk about complex geometry of real aircraft, for example, this is a Eurofighter Typhoon. There are canard, pilot canopy, hard rod, vertical tail, additional bodies and wing tips, air intakes below. And this complex geometry cannot calculate by theoretical analytical method. And we need to use 2 another methods. Numerical methods is a computation fluid dynamics. Maybe you hear about ANSYS software. ANSYS Fluent, for example, this screenshot taken from ANSYS give us possibility to calculate very complex geometry and very complex flow phenomena like separation, laminar turbulent transition, so on. But this software sometimes calculate something very convenient, but this data have nothing common with reality. And last method, this is the experimental. We do model of aircraft, put this model in wind tunnel, and do experiment. Change angle of attack, change side slip angle, change deflection of control surface of aircraft, and measure all forces that act on this model. Experimental method provide you most reliable and credible data over this data asked from you by government certification like American FAA, like European agencies. Some organization exist in Ukraine, exist in China, and exist in every country. And when you create an aircraft, you must to provide a lot of data for government certification. Only after this step you obtain certificate, and only after you have certificate you can sell your aircraft. Without certification you cannot sell your aircraft, and your design you don't use for make money. Only in experimental method you work with real world and real fluid, real air. In these 2 method, theory and CFD, you work with mathematical model. And in experimental method, you work with physical model that made from metal, from glass, from plastic. And this model you put in real fluid. So reality only in experimental. Theory and CFD don't give you real data. And when you development aircraft, you work with all these methods. At initial design, you use only analytical method. Also, we use analytical method for design optimization. When you have more detail, you work with numerical method. And at last stage, when you need reliable data, when you need certification, we work with experimental data. During time, proportion in which we use this method changes. 100 years ago exist only analytical method and experimental method. And experimental method used mostly analytical at first stage. Numerical method, computation fluid dynamic, start only in 70s maybe, when computer improve, when calculation become relatively cheap. Next one, main topic of our courses, the main principle is a principle of reversibility. You have two different pictures and two different situations. In first situation, plane moving, air at rest. Air still, plane have some speed. In this picture, quite different situation. Plane don't moving only air in wind tunnel. And principle states that force acting on a body when the fluid moves around it with constant velocity, this picture, equivalent to the force which a body experiences in uniform and translatory motion in stationary atmosphere. In this case, and in this case, you have equal forces when you have equal size and equal speed. So these principles give us ability to do experimental in wind tunnel. This principle fail only in one case, when airplane situated above screen, like a runway. So wind tunnel enable us to give reliable data for takeoff, or initial stage of takeoff. When airplane at high altitude in air, this method pretty ok. So we have different methods to get data. First part, direct method and reverse method. Direct method, for example, is very simple method of free fall. This picture shows us two situations: fall in air, hammer and feather, and in vacuum. In vacuum, there is no air, there is no air drag, and hammer and feather fall at same time. In air, there are drag and hammer fall first, feather fall next. And we can measure this difference in time. And this difference in time is proportionate to drag forces. So we can just take a very tall building, take different shapes of body, like a sphere, like a cube, like a cylinder, throw it down and calculate time of falling. And when we have different time of falling of different body, we can calculate drag of this body. This is a very simple and very unreliable method, and used maybe 300 years ago when Galilei threw spheres from tower in Italy. This only for illustration purpose. Second method, you can put your model on rocket sled or car. In this case, we have track, we have frame, model. This is a drag shield of Martian space probe, and rocket motor. Rocket motor give us very high velocity, like 3,000 kilometers per hour. And we can do some measure with our model. Third is a rotary stand. It's a very old technique. You have frame that rotate, and you at far end of this frame put your model. This model rotate around single axis, and you can measure some forces. But this unreliable method because rotation stands have high level of vibration, and this vibration affect on measures. And four is a free flight, very reliable and very costly method. You can do free flight with full-scale aircraft, and you must do free flight testing at last stage of your aircraft development. Also, for reduced cost, we can do free flight with scale models. Sometimes this done for very dangerous situation like for stall condition or spin condition, spin recovery, and so on. And reverse method. First and main method and main topic of our course is a wind tunnel. This picture illustrates very simple wind tunnel that used teaching. There are motor in far end of this wind tunnel. We have propeller and motor. This gives us constant flow of air through wind tunnel. This is a test section. We put our model in this test section. We have diffuser that slightly increase cross section from test section to propeller. We have control stand. These blocks of electronics do measure forces of our model, that act of our model, and this intake. And this in intake put screen, phone a comp, and this part is a confuser. This very simple and very cheap wind tunnel we will see at more complex geometry, at more complex and more reliable wind tunnel in future in next hour lessons. Another very simple and similar situation is a hydro channel. Some principles, but in this case we have no air but water. Aircraft put in moving water, and this water act like air. In water you can use what to say in English, paint. Yes, liquid paint that act like this paint show you flow lines of air. You can see pip vortex from canard. This you can see leading edge vortex from delta wing, and this help us understand complex structure of flow around body. And last method, when you interested in a high temperature, in high speed, you just put your model in the jet exhaust of jet engine, and this very useful for simulate, for example, re-entry of space shuttle in Earth's atmosphere, where very high speed and very high temperature. I don't find picture in internet for this method, but I read about it in some old book. Next one, similarity criteria. You don't have ability to put real aircraft in wind tunnel, only in very high size wind tunnel, in very big wind tunnel, and very small aircraft. For example, fighter aircraft, you can put in very big wind tunnel and work with a real scale, but you never put Boeing or another airliner in wind tunnel. In such case, you always work with scale model, with scale down model. And main similarity criteria is a geometry similarity. All dimension of your model must be scaled down at some scale factor. Kinematic similarity, this is about velocity. If in geometry similarity we work with size, in kinematic similarity we must have same velocity with account of scale factor, same point of your model. For example, this point of real aircraft and this point of model, you have exactly same velocity and same angle between vectors with account of scale factor. For example, 10 meters per second, 1 meters per second. For example, 12 meters per second, 2 meters per second. In this case, scale factor 10, and so on. And dynamic similarity, this is about forces. Forces that act on real aircraft and forces that act at model must be proportionality. For example, 10 kilograms, 1 kilograms, 12 kilograms, 2 kilograms. Another very important similarity parameters is Mach number and Reynolds number. Mach number, this is about compressibility, about supersonic, about shock wave around the aircraft. And Reynolds, this is about viscosity. This is related to skin friction drag. This is factor related to flow transition from turbulent to laminar, vice versa, from laminar to turbulent. This factor related to flow separation, so on, and related for maximum lift coefficient of aircraft. Viscosity, Reynolds number, compressibility, Mach number. And you must, for valid experiment, tailor your Reynolds number and Mach number in wind tunnel for flight condition. Look at equation. Reynolds number equal rho. Rho is the density of air. V, velocity of air. L, this is a geometrical parameter, length of aircraft, chord of wind, diameter of fuselage, so on. This is the meters. And viscosity coefficients, mu. Sometimes you work with kinematic viscosity, sometimes with dynamic viscosity. In case of kinematic viscosity, you have only mu. In case with dynamic viscosity, you have rho divided by mu. You have Greek letter nu. In equation of Mach number, you have also v, speed, and a, speed of sound. You have same parameter v in Reynolds and in Mach, but this all parameters different. Mach number independent from size of aircraft. Small aircraft, large aircraft, insect, bird, their Mach number independent of size. But Reynolds number highly dependent of size because you have length in equation. So when you change model scale, you change Reynolds number. When you change flow speed in wind tunnel, we change both Reynolds and Mach. And when you need Taylor, Reynolds, and Mach to flight condition, you have not only size and speed, you have manipulate with density and viscosity coefficient or with speed of sound. How we can change speed of sound? Speed of sound related to ambient air temperature. When you increase or reduce temperature, cold or hot gases, cold or hot air, they all have different Mach number and different speed of sound. In case of density and viscosity, you can change not only temperature, you also can change pressure. When you change pressure, you change density or viscosity, and exist wind tunnel that can change pressure of air. Some experience done with air pressure, some experiment done with pressure that lower than air pressure. This wind tunnel called variable density tunnel, and we talk about this wind tunnel in next hour lessons. Next slide. Our specific task of experimental aerodynamics in aircraft development. First and main our task, this is a measure of aerodynamic characteristic for next development phase. This is a CL, lift coefficient, CD, drag coefficient, CY, side force coefficient, CM, CL, CN, this is a moment coefficient, pitch moment, roll moment, and the normal force and moment, yaw moment. And these 6 numbers we must measure in different settings, different angles, angular position of aircraft, like angle of attack, like side slip angle, different angle of control surface deflection or flap deflection or slat deflection, aileron deflection, rudder deflection, screen presence or absence, screen model our runway surface, and landing gear deployments, drag shooter deployment, brake deployment, air brake, etc. This is our main task. Another very important task, this is a pressure distribution measurement on different aircraft surface. Pressure at wing, pressure at body, pressure at different hatches, doors, or control surface. Next is a measure aircraft characteristic in emergency condition. For example, you lost engine, you lost a control surface, and you must know aircraft characteristic in such condition. Four is a measure stick forces. These forces that act on control sticks, these forces that pilot experience it when you move control wheel, and forces that act on control system, control surface, forces that act on aileron, forces that act on rudder, forces that act on elevator. As elevator and stick connected by control systems, these forces depend also from kinematics of control systems. 5, this is a local aerodynamic refinement. So you change shapes of small different part of aircraft, like fairing between wing and fuselage, like wingtip tanks, like a winglet, and small different parts. and you use visual methods. These methods like uh, like in this picture show pretty examples of visual methods. We put paint in fluid, and this paint show us direction and trajectory of fluid movement. And we can see at these pictures and say, this bad, this good, for example, this we must change shape, ADD some surface or so on, and we put small change in aircraft shapes and look at trajectory of air and make decision about good or bad shapes of some part of aircraft. Next one, sixth task of experimental aerodynamics is a find optimal place for different sensors like pitot, static probes, temperature probes, etc. Maybe I need Google some pictures for better understand this position. Wait a minute. I said about sensors like this. This is the speed measurement. This sensor put an aircraft body. They have different holes, front holes and side holes. This is the static ports and this is the full dynamic ports. And we use manometers, that pressure sensors that measure difference between side ports and front ports, and we can calculate airspeed from this difference. And this sensor must be put in better part of aircraft. For example, at Boeing we have 3 sensors in front part of aircraft. This is the Airbus, and you can see 2 sensors at left side and 1 sensor at right side. And when you design shape of your aircraft, you must to select better place for this sensor. What requirements for this place? First, airflow in place of sensor installation must be don't disturbed by front part of aircraft. For example, this sensor must be put in very front part of aircraft. But in some situation, you cannot put the sensors in nose part. For example, this picture show us Cessna airplane, and small airplane like Cessna have a propeller in nose part, and this propeller very disrupt air. For example, in Cessna, you must put a pitot tube on wing, and different shape of aircraft dictate you better place of installation this sensor. And not only pitot sensor, also angle of attack sensor. In Cessna, you don't have angle of attack sensor like in Boeing. In Cessna, you have small hole and upper part of wing and pressure sensor in this hole. Seven. This is the troop and cargo dropping in air. You must measure trajectory of your cargo and if necessary, made some aircraft shape refinement. For example, return to Google. Maybe I find better picture to illustrate. This one, for example, this is a picture from video, but we can see all necessary features of aircraft design at this picture. So rear end of aircraft have cargo hatch, have ramp, and these two vertical strakes. These vertical strakes create additional vortex, and this vortex improve situation with air, with parachute of cargo or troops. For example, different airplane and some strakes, but more enlarged. If I find a good picture. For example, An-26. This is also rear end of aircraft, cargo hatch, ramp, and also two vertical strakes. This is not for stability and control. These strakes only for air dropping cargo. These strakes create two vortex, air moving from external to internal. And these two vortex, wait a minute, I made small picture. Vortex 1, strike 1, strike 2. This front part of aircraft, wing, so on. But for us important only vortex trajectory. Air moving from this to this. Okay. And we have this vortex. Some with this, but opposite direction. And these strakes create flow vortex. Or I have small error with direction. And when you have something that moving in this direction, this trajectory, and your troops, for example, need deploy parachutes. And these parachutes interact with vortex, and in situation when you need to put two people together in same time, their parachutes must moving in opposite direction. And this vortex create airstream in this direction and help diverge these two parachutes in opposite direction, and these people don't collide in air. Is this for safety of air dropping of people from aircraft? Next one, this is the aeroelastic characteristics, flutter, buffeting, aileron reversal. When you have rigid aircraft, you don't measure aeroelastics, and you need special, very elastic models for this measurement. This different topic. 9, this is a post-stall and spin characteristics. You need special vertical wind tunnel. And 10, this is an emergency landing of water, special equipment like hydrodynamic channel. We have end of time with free version of Zoom. Or maybe we can reconnect after small break.